So welcome back. We're continuing to go through all of our free response questions. I've picked out what I thought was the hardest one today instead of just giving you the first one. We'll see if we can do that together this morning. Okay, so goal is to reconstruct a Taylor polynomial approximation, but this time given a table of values instead of giving a function. So really quickly to review, we've got our comma and Maclaurin series here. The first four of these really are ones that ideally we'll have memorized so that we can manipulate them later. I think I've got these out of order actually. Okay, I'm going to start with this one. So our Taylor series approximation for the nth degree polynomial approximation at some x value would end up being the nth derivative of our original function at that center point times x minus our center point to the nth power over n factorial. So in this case, a is our center point. And then if we wanted our error, I would go to the nth plus 1 degree, so that's my next term. But instead of centering at x equals a, I'm going to maximize whatever that n plus 1th derivative would be. So that means if you were to end up with your next term being a sine function, then I would want to maximize that term as plus or minus 1. So it's as big as this could possibly be for any value that you plug in. Okay, any questions on Taylor series?
Nope.
Cool, let's take a look. So we've got this function h, which has all of these derivatives above. So we've got the first 4 derivatives at 3 different x values. And we're told that h and all 4 derivatives are actually increasing on this interval from 1 to 3. So the first thing we want to do is write a first degree Taylor polynomial for h about x equals 2 and use it to approximate h at 1.9. Okay, so what do we have to do first?
So you have to write a general formula maybe.
Okay, let's start with there. So my nth degree polynomial approximation, we've got a first degree polynomial approximation. So n is 1 for x will be equal to so I'm going to have the sum from n equals 0 to infinity of our function, which in this case is h. So this is the nth derivative at h at our x value. So in this case, okay, we are centering at x equals 2. So let me do that really quick. We were centered at 2. Okay, times x minus 2 to the nth degree over n factorial. Okay, so what's my first term?
First term is 11. No, 80.
First term is 80, okay? So that's the 0th derivative, which means we did not derive, would give us a constant. And because I'm plugging in 2, this is 2 minus 2. For car. Okay, what's next?
128.
Okay, plus 128 times
X minus 2.
X minus 2 to the first power this time instead of 0.
Uh-huh.
Over 1.
What? Yeah.
Okay. So I've got our first degree Taylor polynomial. So we could say our first degree polynomial at 2 would be this.
Mm-hmm.
Actually, I could say this is x. We can plug in whatever x value you want. Okay, so I'm going to plug in 1.9, and we'll see what that gives us. So our Taylor polynomial approximation at 1.9 would be equal to 80 plus
128 times 1.9 minus 2. Mm-hmm.
okay, or 80 plus 12.8.
80 minus 12,
Yeah,
12.8, that's 80, no, 67.2.
67.2. Okay. And then last part of this, I want to know, is the approximation greater than the actual value or less than the actual value?
Greater?
Okay, I disagree, but why? What's your reasoning?
I don't know. I guessed it because the second one is the number and then first one is
Okay, so we were given a little bit more information than just the table, though. For this last sentence, the function h and all four of its derivatives are increasing.
Yeah,
So if that's true, then our approximation should be what?
less than
Right.
the actual value.
Okay, so I could say p1 at 1.9 should be less than h at 1.9 as h prime is increasing on our interval.
Mm-hmm.
From 1 to 3. Oops. I can't erase.
Oh,
There we go. 1, just a delay. Okay, any questions on part A?
nope.
Okay. Okay, part B, write the third degree Taylor polynomial. So I'm going to copy, because we're still at x equals 2, I'm going to copy our first line here, since that's not going to change. So that's 80 plus 128 x minus 2. P3x is equal to 80 plus 128 times x minus 2 to the first power over 1 factorial. And we are still summing up n equals 0 to infinity of h to the nth power at x times x minus a to the nth power over n factorial. Okay, what's next?
Plus 488 times x minus 1 to square divided by 2 factorial.
488.
Over 3.
Okay, 488 over 3 times
x minus 2 square divided by 2 factorial.
Okay, if I want to simplify this a little bit, what can I do?
That's 488 divided by 6.
Okay, I'm going to leave it like that. 48 over 6.
Times that one, x minus 2 square.
Okay, and I need one more term, right? For a third degree polynomial. So
Plus 584 over 9.
hold on, I think we're still in the third term, not the fourth term
Oh,
yet.
yeah. 448 divided by 448 over 3 times x minus 2 cube over 6.
Okay, so what number
So
should
it should
be
be 30. No, 18.
18? There we go. So that's our 3 we originally had times 3 factorial, which is 6. 3 times 6 is 18. Okay, cool. So that's our third degree Taylor polynomial. And then use it to approximate h at 1.9. So I could say h at 1.9 is roughly equal to the p3 at 1.9, which is what happens if I plug in here. I think I'm just going to pull a calculator for this one. Okay. So we've got 80 plus 128 by negative 0.1 plus 48 over 6 by negative 0.1 squared plus 48 over 18 by negative 0.1 cubed. Okay, so we've got 6.36. Okay, that's not what I was expecting, so hold on. If I need to redo these parentheses. Maybe. Nope. Okay, where'd we go wrong? 80 plus 128 x minus 2 plus 488 over 6 plus 448 over 18. Okay, that all looks fine. Approximating at 1.9. 1.9 minus 2 is negative 0.1. That all looks fine too. Plus 1 cubed. Well, I don't see anything. Maybe I did this wrong the first time.
Oh, I think square and cube number should be outside the parentheses. Because you see if it's square inside, that's gonna be negative, isn't it? Because
Oh, okay.
square first.
Yeah, I see what you're saying. So I'm actually Not
So we can
changing,
just say
not changing
positive.
signs here, right?
Yeah.
Okay. You're right, that's my bad. And that's the only one that's going to change, right?
That's one is okay because we have to get negative number.
Yeah, cool. Okay, thank you.
Mhm.
Is that 67.988?
Yes.
Okay, and that does match what I got last time, so that looks good.
Yay.
And then last part, I want to use the Lagrange error bound to show that the third degree Taylor polynomial for h approximates the actual value with error less than 3 by 10 to the negative fourth power. So that means we're going to have to maximize our next term. Okay, so what would my next term have been?
Next term
Mhm.
is 584 divided by 584 over 9.
Okay, so I could say h at 1.9 minus p at 1.9 would be less than or equal to 584 over 9
Over 9
times
x minus 2 fourth power over 432 is 24.
over 4 factorial.
Yes.
Okay, cool. So my error should be less than or equal to that. So I'm going to throw that in my calculator again. So this is 584 over 9 times negative 0.1 to the fourth power. Be a little bit more careful with my parentheses this time. Times 1 over 4 factorial. I think I'm just going to write, this would be 24. Negative 2.7037 times 10 to the negative 10th, or some 10 to the negative 4th. Negative 2.7037. Okay. So that's less than or equal to negative 2.7037. 037. That did repeat there, right? Yeah. Times 10 to the negative fourth power. Okay, and is that less than 3 by 10 to the negative fourth power? Yes. Okay, I'm looking at error here, so this should be in the absolute value while I'm here. On this side too, actually. So our value that we got, negative, positive value 2.7037 by 10 to the negative fourth is less than 3 by 10 to the negative fourth. Okay. I think that's it. It didn't ask us to justify, it just asked us to show. Okay, so I'm going to jump into the scoring guides and we'll see how we did. Jump back really quick. Okay, so for A, we got our first polynomial is 80 plus 128 times x minus 2, and then we are increasing on the interval, therefore our approximation is less than. Okay, scoring guides I'm pulling up now. Okay, so you've got that. Nope, running in white. Okay, I've got our first polynomial. So that's 2 points. Did we find it? 67.2. Yes. Okay, we've got 67.2, and it is increasing. Okay, that's good. 80, 128, 48 over 6. Okay, that's good. 2. And 67.988. Okay, that was one we weren't sure on. Yes. Okay, we got that. Or you got that, rather?
Yep.
Okay, then Lagrange error. Okay, we are maximizing it to our derivative. Yep, okay. And it is going to be less than. Okay, cool. Yeah, we're good. So that's all 9 points.
Yay.
Any questions on anything from today?
Nope.
Okay. So I'm going to have you finish number 1 and 2. They are with calculator this time. For
1
that,
and 2.
yep, 1 and 2 from 2008.
Mm-hmm.
And then we'll be set for today.
Yep.
All right. And I will see you tomorrow for physics.
Bye bye.
Goodbye.